Okay, I'll take care. This is the 13th lecture on Fourier transform of periodic functions and Fourier transform properties. We had last time introduced the Fourier transform, that if there is a function x of t which is Fourier transformable to x of omega, where capital X of omega is equal to minus infinity to infinity the function x of t e raised to the minus j omega t and integrated with respect to t, and its inverse x of t is given by 1 over 2 pi, there is a scaling factor, minus infinity to infinity capital X of omega, then e to the power j omega t, this is minus here, and the inverse transformation it is positive, then the integration is with respect to omega, because we want to find out a function of time. We also considered the question of existence and convergence of the Fourier series. We basically discussed two types of conditions. One is that the signal is an energy signal, and the other is that it obeys Dirichlet conditions. One contains integrability of xt mod squared, and the other contains integrability of xt mod, absolute integrability, in addition to two other conditions on maxima and minima and discontinuities. Alright. Then we had worked out a few examples, and one of the examples was the following. The usual example that we take of a rectangular wave, rectangular function goes from minus t1 to plus t1, and this is 0. Alright, this is my x of t. It is an aperiodic function. It exists only between minus t1 and t1 is 0 elsewhere. And we showed that capital X of omega, by applying the definition, is given by 2 sine of omega t1 divided by omega. This is capital X of omega, and a plot of capital X of omega versus omega is like this. It shows a damped sinusoid type of response on both sides, and the first maximum, well, the maxima occurs at t equal to 0, omega equal to 0, and the value is twice t1. If you take the L'Hopital, that is differentiate both and put omega equal to 0, then the first maximum is at pi by, first 0 is at pi by t1, and the 0 here is at minus pi by t1, and this amplitude gradually decreases as omega goes on increasing. Now the question that I ask now is the following. Exactly like Fourier series, Fourier series contains an infinite number of terms, k equal to minus infinity to plus infinity for a periodic function. Exactly like Fourier series, you see x of t, if I wish to reconstruct x of t from the spectrum, obviously what I have to do is to take the infinite spectrum minus infinity to plus infinity. In the case of Fourier series, it was a line spectrum. In this case, this is a continuous spectrum. I have to take the spectrum and take its inverse Fourier transform. You saw that in the case of the Fourier series, if we truncate the series at a finite number of terms, then we encounter discontinuity, we encounter ripple phenomena, and a phenomena at the points of discontinuity which goes by the name of Gibbs. Now the question is, does something like this happen here? The exact question should be asked like this. Suppose in the other case, Fourier series case, we have truncated the Fourier series. There is no problem, k equal to minus n to plus n. How do we truncate it here? What we say is, let's take only a certain finite range of the spectrum. Let's say we truncated minus w and plus w. This is symmetrical. So we take capital X of omega between minus W and plus W and make the rest of it 0. Alright, which means that the given spectrum capital X of omega, we are not taking from minus infinity to plus infinity. What we are doing is we are multiplying this by a gate, and this gate is in the omega domain, the frequency domain. So it is of the form u of omega plus W minus u of omega minus W. Okay, this ensures that we are taking a chunk of X of omega between minus W and plus W. Alright, let's call this XW of omega. Alright, let's call this XW of omega. What we do now is take the inverse Fourier transform of XW of omega. Alright, and let's call this X small x W of t. Okay, how does, the question now that we ask is, how does X small x sub W of t behave as W increases? Alright, obviously if W tends to infinity, then this should tend to X of t as W tends to infinity. Alright, this should tend to X of t, because W tends to infinity means we take the whole spectrum. But contrary to expectation, this does not happen. Gibbs phenomenon takes over. In other words, what happens is the following, that what we are trying to get from the inverse Fourier transform is this rectangular pulse, but what we get is something like this. At the points of discontinuity, there is an overshoot. In between, at the point of discontinuity, the value is half of the value on the left hand side and the right hand side, and as we exceed the discontinuity, there is an undershoot, and then there are ripples here and here. Similarly, it occurs here and also here. Alright, exactly the same way as in the case of Fourier series. So Gibbs phenomenon occurs also in the case of Fourier transform, and it occurs because there is a point of discontinuity. If the function was smooth, if it was differentiable everywhere, then this problem would not have arisen. Alright, so Gibbs phenomenon does take over. Gibbs, I have written wrongly. The name is Gibbs, so the apostrophe must come after S. Gibbs phenomenon. And you can make quantitative judgments of how much is the overshoot, how much is the undershoot, and so on. And contrary to expectation, even when W is very large, infinitely large, what you get is, instead of a discontinuity like this, you will get a rod like this here. The ripples will be very, very high frequency. You will not be able to distinguish that there are ripples, and there will be a very small magnitude. But at the point of discontinuity, slightly below, if this point is T0, then T0 minus and T0 plus, there will be overshoots and undershoots. Alright, this gives phenomena. The other point that I want to illustrate is the following. That is, suppose we go from the omega domain to the t domain. That is, we consider inverse Fourier transform. For t to omega, you have seen that if we have a rectangular pulse like this, the spectrum, if this is my x of t, then capital X of omega is of the form of sine x by x. That is, it ripples like this, and so on both sides. Suppose I take the other type of approach, that is, we go from omega domain to the t domain, and suppose we have a band limited spectrum. That is, we have a spectrum like this. Now I am drawing an x of omega, capital X of omega versus omega, and the spectrum is band limited to minus W and plus W. Alright, the spectrum is 0 elsewhere. So instead of taking a rectangular pulse in the time domain, I have taken one in the frequency domain. And suppose we go from here to x of t. That is, I take 1 by 2 pi, then I have to integrate only from minus W to plus W, the value, let's take the value as 1, then e to the power j omega t, then integration with respect to omega, d omega. And if you do this, a very simple integral, you will see that what we get is sine of wt divided by pi t. This is what we get. And this is a very interesting phenomenon, namely that if we start with a rectangular pulse in the frequency domain, the inverse transformation again gives a sine x by x form. That is, if I plot this versus t, then all that I get is a maximum, and then it ripples like a damped sinusoid. What I am plotting now is x of t versus t. X of t versus t. The first maximum, the first 0 occurs at pi by w, and this 0 occurs at minus pi by w. The maximum value, what is this? The maximum value? W by pi. W by pi. W by pi. Alright? Now, if you compare this picture with this picture, what is the maximum value here? Twice t1. This first 0 was at pi by t1, and this 0 was at minus pi by t1. Now, if you compare this picture with the rest, then you see that there is an exact duality. This principle is called duality. That is, if there is a time waveform which gives a certain kind of spectrum, now they can, and if you reverse the roles, there is almost a one-to-one transformation. The shape is the same except for, let's say, the amplitude. Well, amplitude is of no concern. You can multiply by any number that I like. xt is multiplied, and therefore there is no question. But it's exactly the same form, sine x by x. And this is the principle of duality, which we shall formally state and prove later when we do the properties of Fourier transforms. Now, this is an example, and such an example occurs in many places in communication engineering, as you shall see later. Let me tell you that in practice, talking about such pulses, and such pulses are simple in a lecture class, but in practice, no spectrum, there is no signal in the world whose spectrum is band limited like this. There is no signal in the world which has a zero rise time like this. And therefore in practice, what we shall have is an approximation to this. But these idealizations help us in designing communication systems and circuits. Now, both of these functions, that is in the time domain, 1 t1 minus t1, the Fourier transform is twice sine of omega t1 divided by omega, and the inverse Fourier transform of this pulse between minus w and plus w, if this is x of omega, then its inverse Fourier transform, as we have just shown, is sine of w small t divided by pi t. Both of these functions go by the common name of a sinc function, S-I-N-C, and sinc function, sinc of x, is defined as, this is just a nomenclature for a function, because sine x by x you will encounter many places, and both of them can be put in this form, sine of pi x divided by pi x. This is the definition of sinc function, and obviously you can write both of them in terms of sinc functions. For example, the first one can be written as sinc of omega t1 divided by pi. Isn't that right? Sinc x is sine of pi x. So I should write this as pi times x, so pi times omega t1 by pi, and the multiplying constant shall be twice t1. In a similar manner, this I can write as sinc of wt divided by pi, and the multiplying constant shall be simply w by pi. Alright, I just wanted to introduce this function, the sinc function, which is of the form of sin pi x by pi x. That's the definition. So both of them can be put in the form of a sinc function. Now we come to the topic of the day, namely Fourier transform of a periodic signal. And in the process we shall encounter some interesting questions, and I shall try to answer them. You recall that in the motivation or the introduction of the Fourier transform, what we basically did was take the same rectangular wave. No, I don't have to. We took a general x of t, alright. Not necessarily rectangular. Let's say we have an x of t which is like this. X of t. It exists between minus t1 and plus t1, and it is 0 everywhere else. Then we said from x of t, if you recall how we proceeded, we create a periodic function, x tilde of t, which is a periodic repetition of the same waveform. A periodic repetition of the same waveform. This is t0 by 2 and minus t0 by 2. And we said that x tilde of t, that is the periodic function, can be written as summation k equal to minus infinity to plus infinity e to the power j k omega 0 and ak, where ak was equated to, what was ak? It is x of k omega 0, where capital X of omega is defined as minus infinity to infinity, the Fourier transform of x of t, e to the minus j omega t dt. Alright. The values of this function was taken at the various points k omega 0. Have I made a mistake? Is this okay? X of k what is it? Yeah, omega shall be put equal to k times omega naught. That's how you get x of k omega naught. Yeah, I think I made a mistake. ak is this divided by t naught. Okay, that's the point that I was missing. Now ak is, well, I could also write this as from minus infinity to infinity. I know my function exists between minus t1 and plus t1. So I could replace these integrals by minus t1 and plus t1. I could also replace by minus t0 by 2 to plus t0 by 2. Isn't that right? It would not matter. Times xt multiplied by e to the minus j omega t dt. But in this range, xt, now try to follow this argument very carefully. I have already explained this, let me repeat. In this range, that is minus t0 by 2 to plus t0 by 2, x of t and x tilde of t are identical, and therefore I could as well replace by x tilde of t. Alright. Now you know that ak, the coefficients in the Fourier series expansion of x tilde of t, summation ak e to the j k omega 0 t, these coefficients in the Fourier series, they could be evaluated over one period, and the location of the period is of no consequence. Isn't that right? We could take from 0 to t0, minus t0 by 2 to plus t0 by 2. We could take from an arbitrary small t to small t plus t0. Alright. This was agreed to, accepted in the Fourier series. Alright, it didn't make a difference where we take the period. Now here obviously it shall make a difference. Isn't that right? That is, if we take from minus t0 by 2 to plus t0 by 2, then we are integrating for x of t. Whereas if we shift the function, if we shift the origin of the time, we take some t0 to t0 plus t0, obviously the x of omega shall be different. Isn't that right? To illustrate the point, let's take the rectangular case again. T1 and minus T1, and the periodic repetition of this is this, T1 minus T1, and then this is 0, then we have this is T0, alright. Now this is T0 by 2 and this is minus T0 by 2. Let's take, for evaluating capital X of omega, let's take one of the integrals as minus T0 by 2 to plus T0 by 2. Then you know what the value is. What was the value? Twice sine of omega T1 divided by omega, right? That's the value if I integrate from here to here, alright, and let's call this x1 of omega. Now if the other interval that we take is from here to here, 0 to t0, obviously the integral shall be different. Obviously the integral shall be different. That is, I shall get an x2 of omega which will be integral from 0, I beg your pardon, I made a mistake here. This is plus t1 and this is minus t1. Alright, it will be 0 to t1, one integral, plus, what is this value? This time t0 minus t1. So plus t0 minus t1 to t0, alright. The integral now shall consist of two parts because in between it is 0. 0 to t1 and then t0 minus t1 to t0. Obviously x2 omega shall be different. You can show, if you carry out this integration, this simple exponential function, so integration is not a difficult process, you can show that x1 of omega is equal to twice sine omega t1 divided by omega, and x2 of omega is quite different from x1 of omega, and the result is the following. x2 of omega is 2 by omega sine of omega t1, exactly the same as this, but unfortunately this is multiplied by e to the minus j, I beg your pardon, it is not exactly this, it is sine omega t1 divided by 2, alright, multiplied by e to the minus j omega t1 by 2, I skip the algebra, e to the minus j omega t0 minus t1 by 2. Alright. So there is a contradiction now. Now which x of omega should you take? After all, what your purpose is to express the given periodic function in terms of Fourier series, and you wanted to express ak in terms of a Fourier transform of one period of the waveform. That is, ak is 1 by t0 capital X of omega. Now capital X of omega is different depending on over which interval, over which location of one period we integrate. It could be x1, it could be x2. Which one should we take? Fortunately, it is not the functional forms that matter. What matters is, if you recall, ak is simply 1 by t0 x of k omega 0. That is, it is a spot value of the function. The functional value at omega equal to k omega 0. And one can verify that capital x1 of k omega 0 is the same as x2 of k omega 0. That is, it doesn't matter where your location of the period is. You can find any x of omega. If you sample this x of omega at values of omega equal to k omega 0, omega 0 is 2 pi over t0, alright, then the values are identical. In other words, it doesn't matter It doesn't matter how you choose your period. You choose your period in the simplest possible manner. Is this clear? This contradiction as to where it should be located? And the answer is, it doesn't matter. Because x1 of k omega 0 for any value of k is the same as x2 of k omega 0. Similarly, you could choose some other x3 of omega, then also it should not have mattered. Wherever you want, you can put the period and integrate. Alright, this is one of the questions, one of the interesting questions that the correspondence between Fourier series and and Fourier transform raises. Next, let us take the case of a periodic function. Let's say x of t equal to x of t plus capital T. Well, let's keep t0. T0 is the minimum value of this constant for which this is satisfied, and let's say it satisfies, this periodic function satisfies the conditions of Fourier series, so that x of t can be written as summation ak e to the power j k omega 0 t, k equal to minus infinity to plus infinity. A periodic function, as I had mentioned earlier, does not satisfy the existence conditions, does not satisfy the sufficient conditions for existence. For example, the Dirichlet condition, the first Dirichlet condition, that is, it should be absolutely integrable, xt dt minus infinity to plus infinity less than infinity. This is not satisfied by a function, for example, like this, a periodic function like this. It continues to infinity. It does not satisfy because the area under the curve goes to infinity. But nevertheless, a Fourier transform exists. That's what we want to show, that it is a periodic function, but its Fourier transform exists provided you admit of an unit impulse function, that is a delta function in the frequency domain. And to show this, if at all this is Fourier transformable, what we should have is capital X of omega should be equal to summation, because it is a linear decomposition, summation k equal to minus infinity to infinity ak. This is the only function of time inside the integral. Ak is a constant, so we shall have Fourier transform of e to the j k omega 0 t. Alright, if we can find this out, then we are sure we have been able to transform. Now let's see if we can find that out. Let's take this function e to the j omega 0 t. To be specific, we admit k equal to 1. Later on we can multiply by k, it doesn't matter. Now for doing this, instead of going directly, one can also go directly, but one requires a little bit deeper knowledge of mathematics to be able to derive the Fourier transform of this. What we do is, we consider a function 2 pi delta of omega minus omega 0. Let's consider a function, let's say, what should we call it, x1 of omega as equal to this. And let's see, this is an impulse in the frequency domain. This is an impulse occurring at omega equal to omega 0, whose strength is twice pi. Alright, let's see what its inverse Fourier transform is, that is x1 of t. What is this? Now, you know that inverse Fourier transform is obtained by 1 by 2 pi, and 1 by 2 pi shall cancel, minus infinity to plus infinity, x1 of omega e to the power j omega t d omega. Alright? Now, if you substitute this, if you substitute x1 of omega equal to 2 pi delta omega minus omega naught, then you see 2 pi and 2 pi cancel. Delta omega minus omega naught exists only at omega naught, and therefore this integral simply becomes e to the j omega naught t. Isn't that right? We are doing it in the reverse fashion, and therefore we have established that e to the j omega naught t and 2 pi delta omega minus omega naught are Fourier transform pairs. Alright, you have to admit of a delta function to be able to take the Fourier transform of e to the j omega naught t. Now my job has become simple. My function was the periodic function was x of t equals to summation ak e to the j k omega 0 t, k equals minus infinity to plus infinity, and therefore capital X of omega shall now be equal to k equals minus infinity to plus infinity 2 pi, I beg your pardon, not ak, okay, 2 pi ak delta of omega minus, instead of omega 0 we shall now have k omega 0. That's it. That's the spectrum, that's the Fourier transform of a periodic function. Now what is the difference? You recall that that if it was in the Fourier series, if it was Fourier series, then its spectrum would be simply the plots of AK versus K. It's a line spectrum, alright? The Fourier series, the spectrum is magnitude spectrum, for example. You plot AK versus K or versus omega. Then you shall have values omega 0, 2 omega 0, k is 1, 2 and so on, alright. It would be a line spectrum, that is you shall have line set k equal to 0, k equal to 1, k equal to 2 and so on. What is the difference here? Well, what you get here, if you plot x of omega versus omega, shall you get a continuous spectrum? No. You also get discrete spectrum, because the spectrum exists only at omega equal to 0, omega equal to omega 0, 2 omega 0 and so on the other side also. At each frequency, however, you don't have a line now, you have an impulse, okay? You have an impulse. Now, the line here would have been of magnitude, let's say A1, whereas the impulse now is of strength, instead of A1 it is twice pi times A1. So there is a scaling factor of 2 pi. Similarly, the impulse here shall be 2 pi A2 and so on both sides. Right? You see the similarity between Fourier series and Fourier transform of a periodic function. In terms of Fourier series, the spectrum is a line spectrum. In terms of Fourier transform, the spectrum is discrete but not a line spectrum. Instead of a line, you have impulses. Let's take a few examples. If you take the familiar rectangular wave function and you extend it periodically, this is 0, capital T1 minus T1, and this is x of t. Let's take the amplitude as 1. Then you know x of t is equal to summation, what is ak? Twice sine, yes, twice sine omega k omega 0, k omega 0 T1 divided by k omega 0 times e to the j k omega 0 t. This is the Fourier series, and therefore its Fourier transform shall be simply summation k equal to minus infinity to infinity. Instead of well, ak shall remain the same. I'll have to multiply by 2 pi. Might have been a mistake. Is this okay? Have I written this correctly? AK, the value of AK. Pardon me. This by T naught. No. That's not. Just a minute. Let me check. No, that's not. It's okay. 2 pi. Oh no, I made a mistake. This would be k pi. AK is 2 sine omega 0 k T1 divided by k pi. Or maybe the factor 2 is not there. AK for a periodic pulse like this was sine of k omega 0 T1 divided by k pi. I think this was the correct expression. The factor 2 came because we wanted to bring omega 0 in the denominator. Alright. Okay, so what happens is we just simply multiply this by 2 pi into this. Then instead of e to the j k omega 0 t1 we get delta omega. I'll write it again. X of t is summation k equal to minus infinity to plus infinity. K is sine of omega